Hello friends, today we are going to talk about the depletion layer. Okay, so as we are much aware of the fact that the depletion layer where it is formed when we are trying to join the P junction with P region with the N region, and at the boundary what is the region, we call it as the depletion region. Okay, depletion region, that the because on the P side there are different types of the majority carriers, on the N side there are different kind of the majority carriers. So polarity is a different one. So at the boundary, junction is formed when there is a recombination of the actually holes and the electrons happens, and that region is called as the depletion region. Now when we are trying to introduce the impurities within it, okay, we are trying to change the impurity concentrations in a semiconductor, and if it is getting abruptly changed, okay, abruptly changing from the something like, okay, from here, okay, suppose there are what we call it as acceptor impurities are there, and on the other side there are donor impurities are there. So what is happening over here, that the acceptor impurities here and donor impurities on this side. That is getting changed suddenly, that is getting changed, because when we are trying to move from here to here, then the acceptor impurities getting changed to the donor impurities, and we can obtain the actually abrupt junction. Okay, so Na is changed to the Nd or vice versa, so that we can obtain the again one sided. Okay, so now we can obtain the abrupt junction. Now if suppose Na is acceptor impurities are very greater than the Nd, okay, that is the donor impurities, then we can obtain the one sided abrupt junction. One sided means one side it is more highly doped and other side it is getting lesser as compared to it. Okay, now let us consider this one sided abrupt junction can be represented with the P plus, means the excessive kind of the acceptor impurities, and then the donor impurities will be the lesser one on the N side, or else we can have the N minus P one sided abrupt junction. It can be just represented like this. Okay, now at thermal equilibrium, means without any kind of the applied voltages or the current flow, so this is nothing but the equilibrium condition or thermally equilibrium condition. Okay, without any application of the voltage, and the current is not flowing through it. Okay, so now the when this without any kind of the biasing at the thermal equilibrium, the Fermi level remains same or remains constant, okay, at that one place. So over the distance it is not getting changed. So dEf by dx is equal to 0, and so I can name it as equation number 1. Now let's try to draw the different kind of the diagrams corresponding to the P-N kind of the junction. Okay, the first diagram, which is for the space charge in the P region and the N region, I am just trying to draw over here. So the first one, the figure, I am just going to draw the space charge distribution. Okay, space charge distribution I am just trying to draw. Okay, here, what is here? I can just draw, this is a P region where there are expected to have the electrons okay, and here is something like, okay, is a region. I will talk about this later word. And generally the width of the P region is always less than the N region, so the area, surface area is, or area is more, so I can call it as this is something like N type of the region. Okay, it is getting some time to draw it. And this region, actually we call it as this region is called as the donor density, and okay, and this is something like a acceptor density. and this region is called as the donor density. It is represented with ND, and here it is NA corresponding to it. Okay. And this is over the space charge X, space X. Okay, and total width of the depletion layer, okay, which is from over here, can have the total width is W1. So I just write down the depletion region within the P region as a WDP, and on within this, okay, this is the region, and on the N region side, this is the WDN. Okay, it gives us the width of this N type of the region. So this is a N region, this is a P region, and then the depletion charge. Okay, depletion charge is nothing but the difference between these two. Okay, so the depletion charge is nothing but the how much is the difference between these two. Okay, now this is something like one of the region, and total depletion is depletion region. Depletion region, and width of the depletion region is represented with the W. Is I have just represented well. This is the one of the diagram which will be required thing. The one more region, the one more diagram, which is nothing but the electric field distribution. Okay, electric field is nothing but the minus dV by dx, or field gradient, how much it is there. And generally what we used to have, generally potential is represented with potential, electric field is nothing but the gradient of the potential, and it is given by this diagram over here in this. Okay, so the width of the potential is, or the width of this depletion region is from the minus WdP to the plus WdN. Okay, and I can just shade this region to understand that, okay, this is electric field. So this is minus curly E, so I can have the electric field, so that will not confused with the energy. Okay, and this area, and area under this is nothing but the area gives us the built-in potential. Okay, built-in potential. Do remember this, built-in potential, that is psi b I. Okay, it is represented with the psi b I. Now, yeah, this is electric field, and this is x on the other axis. Then the another diagram, that is nothing but the third diagram is the potential distribution, where the psi b I, we are just trying to have the psi b I is nothing but the built-in potential. Okay, so now the third diagram which I am going to draw is nothing but the potential distribution within this potential distribution. Okay, now how it is? Potential distribution is quite important one again. So this much potential is, this much potential is psi b p or psi p. Okay, so just psi p. On the y axis is I build potential E 0, this is x axis, and total potential this much is psi b I. Okay, and above this potential is psi n. Okay, psi n, I can call it as a minus psi n, because it is negative one. minus psi n. Yeah, and the last diagram, which is quite again important one, is nothing but the energy band diagram. Okay, energy band diagram. Energy band diagram, that is EK diagram generally we used to call. So I just try to draw this diagram here as well. Actually, which if we are having the PN region, then it would be better to draw, but it is on the overlap side. So I am just trying to plot it something like this. Then sorry, it should have been gone like this. Okay, and there are very much some quantities are there. Okay. So I can call this as a Q phi F. Okay, just wait a moment, let me Q phi P, then this is EV, valence band energy, this is EC, then the some intermediate state, it is represented over here with the dashed line. It goes like this. Intrinsic energy level you can have. Then above this potential is Q phi BP, Q phi BP. Everybody's explanation is in the next contest, so be there with me for some time. Then this potential is Q psi P, and other remaining potential on the Q phi N on this side, on this is Q psi P, and what it is, and here this is nothing but the Q psi BI, and the remaining potential similar like here, this is nothing but the Q phi N, and this potential is nothing but the Q phi B N. This almost potential is minus of this, and this is plus on the upside. The upside is Q phi B N touching over here. So, and yeah, Fermi energy level is at this point, EF. So now, yeah, these are the some diagrams which are much more important to discuss this. So the built-in potential, okay. So the built-in potential here, I am just going to write down from the above this diagram only. Built-in potential, that is nothing but the psi bi, or it is also called as the diffusion potential. Okay, diffusion potential. Probably if you remember this, when we have seen the diffusion phenomena. Okay, so from this, that is Q phi bi, okay, this is potential I am just trying to write down. This is nothing but the total is how much is total is Eg. From that, how much we have to make it minus? How much we have to make it minus? That is nothing but the q phi bn, q phi n, q phi bn. Then the other potentials are something. Okay, we have to just subtract it. So Eg minus q phi n plus q phi p. These potentials we have to make it minus. So q phi n and q phi b. From this we have to make it minus. So that will give us the total psi bn. Sorry, this is q psi bi, built-in potential. So now I can call this is nothing but the, and this is equal to the q psi bn plus q psi bp. Okay, this is equal to q psi b is equation number 2. Okay, so Eg minus q phi b phi n plus q phi p, or else this can be equal to the q phi bn plus q phi bp. Okay, so for the non-degenerate case, for the what we call it as for the non-degenerate case means if we are having the lightly doped semiconductor, psi bi. Okay, so I can write down the psi bi. Just take the q on the other side, and this is some standard relation kt by q into ln of n o upon ni plus from the, this is from the diffusion relation or diffusion potential, kt by q ln of p n o upon ni. Sorry, PPO, not PPO. So this is equation number 3. Yeah, so just try to rearrange the terms in it. So kt by q common, so ln n o PPO upon ni square. So this is equation number 4. But as we know that the what it is, NNO into PPO is equal to Ni square, we know. Also what it is, that is nothing but the PPO into the NPO, NNO and PNO, then PPO and NPO is equal to also Ni square. So try to substitute this value in the above equation. So built-in potential psi bi is equal to kt by q ln of nno upon npo, or else we can have the other equation as well, that is kt by q ln of PPO upon PNO. So such a kind of the relation can be also written down. Now, yeah. So let's have the one more relation corresponding to it is nothing but the psi bi is equal to kt by q ln of, because we can have the nn0 as equation corresponding to an np0. So na into nd, na and nd upon ni square. So this is also the one of the equation for the built-in portion. So this relationship between the carrier densities on the either side of the junction. Okay, so we can have the carrier densities on the one of the equation, on the other side we will be having the potential. Okay, on the potential. So in a thermal equilibrium, the electric field in the neutral regions of the semiconductor must be 0. So at or else, okay, in a thermal equilibrium, okay, in thermal equilibrium, the electric field, okay, that is field in the neutral regions, in the neutral region in the sense that the within the depletion region where the charge is getting recombined, neutral regions must be 0, So means the total number of the negative charges per unit area on in the p side must be precisely equal to the total positive charges per unit area in the inside region. Yes, this is something like here. For total number of the negative charges on the p region must be equal to the total number of the positive charges on the n region, and that per unit area gives us the total neutrality condition. So that will give us the Na, okay, that is a accepted density, impurity density into the WdP on the p side is equal to Nd is donor impurities into WdN, capital N. Okay. So this actually gives us equation number 7. So from the Poisson's equation we can obtain from the Poisson's equation. What is Poisson's equation? That is nothing but the gradient of the electric field gives us the corresponding charge density. So what we can have, dE by dx is equal to rho by epsilon s. Rho is a function of x because we are talking about the one dimensional case, and we know the electric field is nothing but the rate of change of its potential. And how much is potential? The negative rate of change of the its potential. So we can write down the d2 psi bi with having the negative sign by dx square is equal to rho of x upon epsilon s. So yeah, now try to substitute the values of the density. Okay, density, yeah. So minus d2 psi bi by dx square is equal to q by epsilon s into nd plus of x minus n of x minus n minus na minus of x plus p of x. Okay, this is equation number. It means this is something like, okay, yeah, here I am just talking about what is the first term in our equation. That is nothing but the nd plus of x, means here we are having the higher density of the higher impurity concentration of the donor one, okay, and that is excessively doped. Minus n of x, how much amount of the n of x on the present on the n region, okay, that is the carrier concentration of the electrons, minus then the means here we are just dealing with nd plus on the donor side. So nd plus is more one minus n of x, means how many number of the electron concentration on this side, minus of this how much amount of the acceptor impurities on this side, minus the whole concentration present, because see why we have made it minus sign, or p of x and the n of x, because the how much amount of the what we call it, the electrons are present on the this excessive doped donor impurities, they it will get recombined, and whatever is the remaining amount of the charges carriers per unit volume are just considered. Similarly here, so that difference gives us the excessive charges. That difference will give us the excessive charges. So minus d2 psi I by dx square is equal to q upon epsilon s, and this difference. So the inside the deflation region, what happens that, okay, inside the depletion region, what will be the carrier concentrations on the both the sides, okay, because inside the deflation region almost that electrons and holes get recombined. So the n of x is almost equal to the p of x must be 0, because this is something like a complete ionization. So assuming the complete ionization, assuming here that the complete ionization, okay, here we are assuming the complete ionization. Okay, so now, so substitute these values in the above equation. So what we can get it, minus d2 psi I by dx square is approximately equal to q times n a upon epsilon s for p region, that is wdp, which is x, which is less than x, only within, this is for the p region, okay, I can call it as a p region or p side. Similarly, what we can have, d2 psi I by dx square is approximately equal to q times nd upon epsilon s. There must be the minus sign, so plus sign, because minus sign gets plus sign. So what we can have, so this gets by, this is getting, because this goes 0 and this also goes 0. So for this region